Okay, here we go, video 3. So in this one, on polynomial functions, we are going to match each function on the left with its type that is on the right. So when I do this, I start to look at the rates of change. So I can tell here on 26 that doubling is going on. This is all times 2. So doubling, when you have a multiplier that is exponential. So this one is b, 27. So let's take a look, and let's start to take a look at the rates of change on 27. Now, I can just kind of tell from looking at this that this number is this number cubed. So 2 to the third power is 8. 3 to the third power is 27. Now, if you can't just look at it and do that, you can also examine the rates of change. So my first difference is 1, 7, and 19. My next difference is 6 and 12. And then my next difference is 6 in here. So I don't really get to my constant until the third difference. So if you were to continue this table on, you would see that you would get 6 all the way down along here. And since it's the third one over, it's cubic, 3. So this one is D. Number 28. So for 28, we got 0, 1, 2, and 3. And then over here, it's the only one that doesn't have a 0, which is kind of a giveaway. So the reason that it doesn't have a 0 is because this one I can spot as a logarithm. Okay, the only other thing that it could be is linear, like adding 1 each time, but these over here are exponents, okay? So this one is actually log 2x is equal to y. So these are the y values, or these are the exponents, okay? Remember, as an exponential, this would be written 2 to the y is x. So 2 to the 0 is 1, 2 to the first is 2, 2 to the second is 4, and 2 to the third is 8. Okay, so that one is logarithmic, and that is E. And again, my big hint for that one is the input values, or the exponents, go 1, 2, 3 over there. That kind of tells me that that might be a logarithm. And also 0 is not included anywhere in the table, which of course would be impossible because when you have an exponent, you can't get 2 to some power and end up with 0. Okay, that's not possible because 2 to the 0 power, for example, is 1. Right? So that's kind of how that one works for 28. Going on to 29, let's start to look again at rates of change. So this one, it looks like we're going up 1, up 2, and up 3. And then our constant is up 1 each time. So here's my first difference and my second difference right there. Okay? So that must be to the second power, and this one is going to be my quadratic. And then down here, we're going up 1 each time. So we're going to have 1, 1, 1, and 1, like that. My first difference there is my constant, so it must be to the first power, which is linear. Okay, so that one goes B, D, E, C, A, 31. Which of the following functions is a polynomial? Okay. So there's some memorization that you have to have in here, and there was a mistake in our module where this was said to be a polynomial, but it is in fact not a polynomial. Absolute value functions are not polynomials, so that one's out. Exponentials are not polynomials. That one's out. Logarithmic functions are not polynomials, so that one is out. Now for A, it can be, you might think that this one is not because of what we learned about rational expressions. So remember, what we're doing now in 4 is when we have a rational expression like this with a polynomial, with an x value on the top and on the bottom, okay, this would not be okay. But the way this is written right here essentially is the same as saying like 1/2 x, which is a polynomial. So this one, the answer is A, and the main takeaway there would be that, you know, logarithms, exponentials, absolute value functions are not polynomials. Which of the following is not an even function? So remember, if a function is even, a couple things about this. First of all, visually you can spot it because it's symmetrical on the y-axis, okay? So if I have an absolute value function like that, that one is, it's still a function, the way that it's written. It's not a polynomial, but it would be even because it's symmetrical on the y-axis, okay? So we need to start thinking about which of these graphs wouldn't be. So for A, when you have the absolute value of x, it looks like that. And for B, with 3x squared, remember that 3 doesn't move it anywhere, okay? It just changes our stretch. This is actually going to be our answer because this one, this minus 5 is a shift 5 to the right. Okay, and then lastly, we're going to have negative x to the 4th, and then we have this 3 hanging out in front, so it might be helpful for you to think about it as negative x to the 4th plus 3, which of course would be the way that it is written there. This would be a shift. This would be a shift up 3. Okay, so that takes us through problem number 32. And now we're getting on to problem 33. Find all the roots of the equation. Okay, I got a little repetitive in here, and this isn't exactly on the test, so I'm only doing number 33 here. So when you have this, we want to think about what one of the roots is that we could find pretty easily. So we know that with these, this is equal to 0. So if I were to solve this for one of its simple roots, I would take away 1 from both sides, and I would get this. And then if I took the cube root of both sides, I would get the answer is negative 1, because negative 1 to the 3rd power is equal to negative 1. And if you just think about it like that, when I multiply those together, I get negative 1. So one of my roots, one of the 3, and again, there has to be 3 because it has to match the degree of the polynomial, but one of those roots is going to be equal to negative 1. So now I start thinking about factors. So for factors, if I have a root of negative 1, that means it has a factor of x plus 1. So to get the other factors, I could divide it into the polynomial. So I have x plus 1 divided by x to the 3rd. And I'll explain that in a minute if you don't know, but my sense is that most of us do. Oop, that should be 0x. Okay, and then we're going to divide in. I'll use a different color. So this will be x squared, and then we'll have x to the 3rd. And then we're going to have x squared. So these are placeholders here, okay? Because I have to fall in descending order by degree. So it has to go 3, 2, 1, like that, okay? So when I subtract here, what do I get? Oh, this is squared. I get negative x squared. And then that would be plus like 0x, right? And then I would divide here. And I'm going to get... so negative x squared divided by x is going to be negative x, and I'm pretty confident on our polynomial long division, so I'm not going to talk us through this too much. But here I would get negative x squared, and then negative x. It's getting kind of jumbled there, so I'm going to rewrite this actually right here, just so it's a little clearer. So negative x squared plus 0x. And then I had minus x squared minus x. and that's going to give me 0, and then I'm going to have 0x minus a minus s is positive x plus 1, and then now I'm dividing this and this, remember, giving me plus 1, and when I multiply through, everything's going to go away, and remember with these, you should not have a remainder. Okay, when you're finding roots, there's no remainder. So now I have this trinomial right here, and it's pretty easy from here to get its factors. So I'm going to erase some of what I have here, because I don't have a ton of room on this one. I may go down into here, actually. So let's take x squared minus x plus 1. So this one does not factor nicely, so you have to use the quadratic formula, where a is 1, b is negative 1, and c is 1. And then we're going to have negative b plus or minus the square root of b squared minus 4 times a times c, all over 2a. Okay, now we're going to break down the square root of negative 3. So remember, that would break down to the square root of 3 times negative 1. And the square root of negative 1 is I. Now, that was covered mostly in AGS 2. And I'm feeling pretty good that we know that right now. So that is going to come out here as I. So this is equal to I times the square root of 3. So what I have is 1 plus or minus I times the square root of 3 over 2. Okay. So that is one of our, those are our other two roots. So we had this one, and then we have these two right here also to finish it off. Okay, going on to 34, this will be my last one on this video. So this one says as x approaches negative infinity, we have some things going on. So what I always do is I draw a graph like this, and then I think about, as I go towards negative infinity, I'm going towards positive infinity, and as I'm going towards positive infinity, I'm going towards negative infinity. So this is what my graph looks like. And then, now that I kind of have a rough sketch of it drawn, I need to decide which one is going to behave like that. So when they're heading in opposite directions, it's not going to have an even exponent. So these two are out. So it's got to be one of these last two. So I see here that the coefficient of this one is negative and this one is positive. So think about something real simple like x to the third power, which we know looks like this. And that's what happens when the coefficient is positive. If I make this like negative x to the third power, we're going to switch, and it's going to come over here like this. So I can see that this one is looking a lot like that. So this must be with an odd exponent with a negative coefficient.